Welcome back, grade 10s. In today's lesson, we're going to continue learning about electric circuits. And in this lesson, we're going to focus on parallel circuits. So we're going to look at rules of parallel circuits. And in a parallel circuit, the resistors are connected in parallel. Now, if you're asked to calculate the total resistance or equivalent resistance or effective resistance, it all means the same thing. You're being asked to calculate the total resistance. And in a parallel circuit, we can calculate the total resistance as 1 over RT equals 1 over R1 plus 1 over R2, etc. Now that's a bit confusing. Remember that in a series circuit, we simply add up the values of the individual resistors. But in a parallel circuit, the calculation for total resistance is not that simple. We have to apply this formula. The implication of this formula is that every time we add another resistor in parallel, we end up getting a final answer that is a lower value. So that means that in a parallel circuit, the more resistors are added in parallel, the lower the total resistance. Also note that the total resistance will always be a lower value than the value of the resistor with the lowest resistance in the circuit. Let's take a look at an example that demonstrates this. So here we have a parallel circuit with two resistors in parallel. One resistor has a value of 2 ohms and the other resistor has a value of 3 ohms. So if we apply the formula 1 over RT equals 1 over R1 plus 1 over R2, then we get 1 over RT equals 1 over 2 plus 1 over 3. You don't need to worry about figuring out the lowest common denominator. You're just going to plug this into your calculator, and your calculator will give you a fraction. So 1 over RT is equal to 5 over 6. Now that we have this fraction, we need to flip it because 1 over RT is 5 over 6. But we want the value for RT. RT is equal to RT over 1. So what we're doing is we're flipping this to make this RT over 1, which is equal to RT. Therefore, we need to flip this fraction to get 6 over 5. And once we have our final fraction, we can get an answer to 2 decimal places. So 6 divided by 5 gives us a value of 1.2 ohms. And just note that this value of 1.2 ohms is lower than the value of the smallest resistor, which is 2 ohms. Now we are going to add another resistor in parallel. So we had a 2 and 3 ohm resistor above, and now we're going to have a 2 ohm, 3 ohm, and 10 ohm resistor in parallel. And we're expecting our total resistance to decrease because in a parallel circuit, as we add more resistors in parallel, the total resistance goes down. So we're going to apply the formula 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So that's 1 over 2 plus 1 over 3 plus 1 over 10. And you're simply going to plug that into your calculator and you are going to get a decimal of 14 over 5. But remember that that 14 over 5 is 1 over RT. So you need to flip the 1 over RT to get RT over 1. So you also need to flip the 14 over 15 to get 15 over 14. And now you can divide the two to get a number to 2 decimal places. When we had two resistors of 2 and 3 ohms in parallel, our total resistance was 1.2 ohms. But now that we've added a third resistor in parallel, we can see that our total resistance has gone down to 1.07 ohms. Again, note that the total resistance is always going to have a smaller value than the value of the smallest resistor. So let's come back to this slide and see if it makes more sense now. Remember that we can work out the total resistance in a parallel circuit using this formula. And in a parallel circuit, the more resistors are added in parallel, the lower the total resistance. And also note that the total resistance will always have a smaller value than the value of the resistor with the lowest resistance in the circuit. In any circuit, the total voltage is provided by the cell. Now, in a parallel circuit, the total voltage is equal to the voltage across each branch. Now, in grade 10, we generally look at problems where there's only one resistor on a parallel branch. And in grade 11, we look at more than one resistor on a parallel branch. The implication here is that the total voltage is equal to the voltage across each branch. Regardless of the strength of the resistor, the voltage across the resistor or across the branch where that resistor exists will be equal to the total voltage. Here I have a voltmeter. If I place this voltmeter above the cell, and let's say it reads 5 volts, that means that the total voltage provided by the cell is 5 volts. Now, the electrons are going to be pushed out of the cell and they are going to run around the circuit. But when they get to the parallel branches, the electrons are going to split into this branch and into this branch. And each electron really has the full amount of voltage from the cell to get across its branch, regardless of the size of the resistor. So here we have a 2 ohm resistor and here we have a 3 ohm resistor. The volt reading across the 2 ohm resistor will read 5 volts, and the volt reading again across the 3 ohm resistor will also read 5 volts. If we come to this circuit over here where we have 3 resistors in parallel, if the cell's voltage is 5 volts, then the voltage across the 2 ohm resistor will be 5 volts, and the voltage across the 3 ohm resistor will be 5 volts, and the voltage across the 10 ohm resistor will also be 5 volts. This is confusing. However, it makes calculations around parallel circuits really easy, because if you've got your total voltage, then you automatically have the voltage across each branch. So this should make quite a lot of sense now, that the total voltage is equal to the voltages across the resistors on each branch. And regardless of the strength of the resistor, the voltage per branch is going to be equal to the total voltage. We already learned that in any circuit, the relationship between resistance and current is inversely proportional. But what we know is that in a parallel circuit, as we add more resistors in parallel to the circuit, the total resistance goes down. Therefore, what happens to the current? Well, the current will go up. It will increase. In a series circuit, every time we add another resistor, the total resistance goes up, so the current goes down. But in a parallel circuit, every time we add a resistor in parallel, the total resistance goes down, and so the current goes up. In a parallel circuit, the current is not the same wherever you measure it. So we're going to have the total current that leaves the cell, and we're going to have the total current that enters the cell. But at the parallel branches, the current is going to split. If we add up the currents among all the parallel branches, then that will give us the total current. If the resistors are identical, then the current will divide itself equally across the branches. But if the resistors are not identical, then we won't have an equal distribution of the current among the branches. Remember that the relationship between resistance and current is inversely proportional. So if I have a branch with a higher resistance, it is going to have a lower current. And if I have a branch with a lower resistance, then it is going to have a higher current. So remember that this inversely proportional relationship between current and resistance applies to series circuits, it applies to parallel circuits, and it also applies to just a branch within a parallel circuit. Because the current will divide itself across the branches of a parallel circuit is also known as a current divider because it divides the current. Again, the reason that a parallel circuit is known as a current divider is because the current will split across the branches. So if the total current in this parallel circuit is 6 amps, assuming that the three resistors are identical, then the current will split equally across each branch so that each branch gets 2 amps of current. If we consider this parallel circuit over here, A1 and A5 are measuring the total current. So before the current splits and after the current has come together, that is where we would be able to measure the total current. But at the branches, the current is going to split. Now, because these three resistors are not identical, we have 2 ohms, 3 ohms, and 4 ohms, A2, A3, and A4 are not going to be identical values. A smaller resistor will get a greater current, and a greater resistor will get a smaller current. However, if I add up the value of A2, A3, and A4, I will get the total current at A1 or at A5. Let's now demonstrate all those rules of parallel circuits by considering the circuits below. So we have circuit A and we have circuit B. Circuit A is identical to our previous circuit A, where we have a 2-volt cell, a 2 ohm resistor, and a 1 amp current. But then we also have circuit B, and in this case we have the same cell of 2 volts. We have a 2 ohm resistor, but we also have another 1 ohm resistor connected in parallel with a 2 ohm resistor. And in this case, we can see that our total current is higher. It is 3 amps. And we can also see individual currents across the branches, which are not identical because the resistors are not identical. What is the total resistance of circuit A? Well, in circuit A, we have 1 resistor, and that 1 resistor has a total resistance of 2 ohms. What is the total resistance of circuit B? Well, this requires a calculation, and because the 2 resistors are in parallel, we are going to calculate it as 1 over RT is equal to 1 over R1 plus 1 over R2. So that's 1 over 1 plus 1 over 2. And without having to find an LCD, just by plugging in these values into the calculator, we get an answer of 3 over 2 for 1 over RT. But we need to flip it. So RT is 2 over 3, which we need to get a number to 2 decimal places, is equal to 0.67 ohms. So in circuit B, the total resistance of a 2 ohm and a 1 ohm resistor connected in parallel is 0.67 ohms. The total resistance of these two resistors is a lower value than the value of the smallest resistor here, which is 1 ohm. So from this, we can see that in a parallel circuit, the more resistors we add in parallel, the lower the total resistance. We also learned that in any circuit, the total voltage is provided by the cell. What is the total voltage in circuit A and in circuit B? It is 2 volts in each circuit. Zooming in on circuit B, what is the voltage across the branch with a 1 ohm resistor? So we know that in a parallel circuit, the voltage across each branch is equal to the total voltage. So it will be 2 volts because in a parallel circuit, Vt equals V1 equals V2. And what is going to be the voltage across the branch with a 2 ohm resistor? Well, recall that it is still going to be 2 volts because in a parallel circuit, Vt equals V1 equals V2. Remember that the strength of the resistors doesn't make a difference. The voltage across each branch will be the same as the total voltage of the cell. In a parallel circuit, the current is not the same wherever you measure it because the current splits at the branches. What is the current across each of the branches in circuit B? We were given these values, but we need to prove it by calculation. We know that across this branch, our voltage is 2 volts and our resistance is 1 ohm. And we know that across this branch, the voltage is 2 volts and the resistance is 2 ohms. And that allows us to work out the current. We are going to use the formula I is equal to V over R. For the 1 ohm resistor, the voltage is 2 and the resistance is 1. So we get a current of 2 amps across this branch. And for the branch with a 2 ohm resistor, I equals V over R, which is 2 volts divided by 2 ohms, which gives us a 1 amp current across this branch. Now note that the branch with a bigger resistor gets a smaller current and the branch with a smaller resistor gets a larger current. The reason being that the relationship between resistance and current is inversely proportional. Also note that if we add up these two currents of 2 amps and 1 amp, that will give us the total current in the circuit. The total current exists before and after the split. So what is the total current in circuit B? We can calculate this in 2 ways. So one of the ways is the way that I just mentioned. We can say that the total current is equal to I1 plus I2. We just add up the individual currents across the branches. So it is 2 plus 1. So that gives us a total current of 3 amps. But the alternative is to use the formula I equals V over R. Now the total voltage in our circuit is 2 volts. But in order to work out the total current, we also need to use our total resistance. And the total resistance of the 1 ohm and the 2 ohm resistors together, we already calculated to be 0.67 ohms. So we're going to say 2 divided by 0.67, and that again gives us the same answer of 3 amps for total current. In any circuit, the relationship between resistance and current is inversely proportional. Explain this based on the circuits above. Now, what we can see is that in circuit A, we have a total resistance of 2 ohms and a total current of 1 amp. But in circuit B, the total resistance has gone down. So it's gone from 2 ohms in circuit A to 0.67 ohms in circuit B. And so when the resistance went down, the current went up. So that shows us that the relationship between resistance and current is inversely proportional. That brings us to the end of the rules of parallel circuits. In the next lesson, we are going to put all the concepts together and we're going to go over some past paper questions.